The sun's surface is a chaotic environment of plasma and magnetic fields, often erupting in active regions, sending massive bursts of energy toward Earth. In 1989, one of these solar storms triggered a blackout across Quebec, leaving millions of people without power for 9 hours. This chart compares the standard safety threshold for power grids against the measurements recorded in Maine during that storm. While the industry considers 1 volt per kilometer a serious threat, the ground in Maine reached an amplitude of 22.79 volts per kilometer. This spike suggests that the danger of a solar storm is influenced by more than just the sun's activity. It depends on how the Earth itself amplifies that energy. There is a mismatch at the core of our infrastructure. Power grids are engineered strictly for alternating current, but solar storms induce sustained direct current into the system. This direct current surge causes massive industrial transformers to saturate, leading to rapid overheating and destroying expensive, hard-to-replace equipment. Historically, grid operators had to rely on simplified, one-dimensional models to estimate these risks. These models failed to account for the complex ways electricity moves through the different layers of the Earth's crust. We were operating a nationwide electrical network while remaining blind to the specific pathways of the planetary circuit right beneath our feet. When a coronal mass ejection hits Earth's magnetic field, the interaction transfers energy downward, inducing electrical currents that travel deep into the ground. To track these currents, the USMTArray project spent 18 years installing 1,800 data stations across the United States. These stations collected magnetotelluric data, measuring natural variations in the Earth's electric and magnetic fields to map the electrical resistivity of the subsurface. This data allowed scientists to model the Earth's interior not as a solid mass, but as a complex electrical schematic. The project revealed that the deep Earth is a three-dimensional network of varying conductive properties rather than a uniform structure. Underground fluids, magma, and ancient geological formations act as highly conductive pathways, cutting through layers of more resistant rock. Induced currents from a solar storm follow these specific pathways. The electricity surges through the conductive materials and bypasses the resistive areas entirely. This creates highly localized risks. A town built above resistant rock might be unaffected, while a neighbor situated over an ancient subduction zone could experience a massive electrical surge. The impact of space weather on a specific power line is ultimately determined by the arrangement of conductive minerals buried billions of years ago. The data from this 18-year survey now feeds into real-time risk maps managed by NOAA and the USGS. Instead of relying on estimates, scientists can pinpoint exact, localized electric risks as solar storms unfold. This precision allows grid operators to isolate vulnerable equipment or adjust loads before the ground-induced currents can cause damage. We have moved from simply detecting solar activity to predicting the specific pathways it will take through our infrastructure. This map of electrical resistivity also provides a record of how the North American continent was originally assembled. By tracing these electrical signatures, researchers can see the conductive scars left behind by ancient landmass collisions. These same conductive signatures are now being used to identify new sources of geothermal energy and hidden mineral deposits. By mapping the billion-year-old geology beneath the United States, scientists built the model necessary to manage the modern electrical effects of the sun.